Hello students, so welcome to my another video. Now today we are going to discuss about a problem regarding a ball rebounding from a wall. Now this topic belongs to the chapter of Newton's laws of motion from class 11. Okay, now those who are watching this video, I hope you have a thorough understanding of the chapter vectors, because to understand this one you need to understand vectors first. Okay, so let's start. So a ball rebounding from a wall. Let us consider that this is a wall. Okay, so this is a wall and I have thrown a ball at an angle. So this is the ball which I have thrown to the wall at an angle. Okay, how much angle? Let us draw a perpendicular to the wall. So this is a perpendicular to the wall. Now I have thrown the ball at an angle theta. Okay, so the ball is thrown at an angle theta with the perpendicular to the wall. So this is the direction of the ball. Now suppose the ball rebounds back from the wall. So this is the ball which rebounds back from the wall, making the same angle theta. Right? Suppose the initial velocity of the ball is v, okay, and the final velocity of the ball is also v. Now over here we are considering that there is no loss of energy, okay, during collision with the wall. Now in practical cases, all of you know that when the ball will collide with the wall, there will be some loss of energy. Okay, so of course if I throw with a velocity v, the ball might not bounce back with a velocity v over here. But suppose we are considering that there is no loss of energy over here and the ball rebounds back with the same velocity from the wall. Fine. Now what we have to calculate over here? You have to calculate the change in momentum of the ball. So you have to consider, you have to calculate the change in momentum of the ball. That means how much change in momentum of the ball occurred due to the fact that when the ball collides and rebounds back from the wall. Fine. Now by seeing the diagram, I hope you can understand that this is a two-dimensional motion. Okay, so this is a 2D motion. This is not a one-dimensional motion. This is a two-dimensional motion because you see, you can understand that the motion of the ball is in both x-axis and y-axis. If I consider this to be the x-axis, this one to be the y-axis, so the motion over here is in both the axes, x-axis and y-axis. So this is a two-dimensional motion, and that is why in the beginning of the video I said that you need to have a thorough understanding of vectors. Fine. Now, so let us first calculate. So first, when the ball is coming, okay, the initial condition of the ball when the ball comes and hits the wall. So first I am going to divide this velocity into two rectangular components. So I am drawing the diagram separately. If you want, you can draw the diagram over here also. So this is the ball, okay, that is coming with a velocity v. Right? So this is the ball that is coming with a velocity v. So this vector I am dividing into two rectangular components. So this is one component, this is another component. Just same over here like this. So here and here. Okay. So this particular thing I have drawn separately for you. Now see, if this angle is theta, this one also will be theta. Okay. So this is theta. Now you can understand, if this is theta, this will be v cos theta. Those who know vectors, those who know rectangular components of the vector, so you will know the component with which I have made the angle, that particular component comes with cos theta. So if this is v, this is theta, then this one will be cos theta, and this one will be v sin theta. Okay. Now while returning back, okay, this is while coming. While returning back, this was the ball. This was the velocity v. So this one again I am going to divide into two rectangular components. So this is one component, this is another component. Fine. Just like over here. So this is one component, this is another component. Now see, if this one is theta, this one also will be theta. Why? See, these two are corresponding angles. Okay. Over here, these two are interior alternate angles. You know, interior alternate angles are equal. These two over here, they are corresponding angles. So if this is theta, this one also will be theta. Okay. So this one will be v cos theta. This one will be v sin theta. Right? So how am I going to write the velocity? So initial velocity. See, I am going to write the velocity in vector form. Okay, I am going to write the velocity in vector form. Now I am going to take both the x-axis and y-axis together. Okay, so I need I cap and j cap, the unit vectors. Now remember one thing over here. If we go towards the positive x-axis, we write it with plus I cap. If we go towards the negative x-axis, we write it with minus I cap. Those who don't know, for them I am writing. If we go towards the positive y-axis, we write it plus j cap, and negative y-axis minus j cap. So this thing remember while writing this one. So v I cap. You know that any vector can be written in this way. Suppose vector A, I can write ax I cap plus ay j cap. So any vector can be written in this way. Those who don't know vectors, I hope please go through the chapter of vectors before seeing this video. So any vector can be written in this way: ax I cap plus ay j cap. That is the magnitude along the x direction into I cap, and plus the magnitude along the y direction into j cap. Okay. So vi, you see, vi, that means, now what is I? I means initial. Okay. I over here means initial. Don't get confused with I over here. I means initial. That is the initial velocity. So initial velocity, I am going to write it in terms of rectangular components. Okay, the initial velocity I will write in terms of rectangular components. How to write in terms of rectangular components? Just see this. Just see this formula over here. Just seeing this formula, we can write over here. Now see, what is the velocity along the x-axis? Okay, what is the velocity along the x component? That is v cos theta. V cos theta. Okay. Now see, this is along the positive x-axis. This v cos theta is along the positive x-axis, and in positive x-axis we use I cap. So I cap plus, okay, ay. Fine. So what is the velocity along the z-axis? That is the y-axis. What is the velocity along the y-axis? That is v sin theta. V sin theta. Now see over here, we have to write j cap. Okay, we have to write j cap. Now on this side we use minus j cap since it is on the negative y-axis. So we are going to use minus j cap. So minus j cap. So this is the initial velocity. You see the velocity I have written it in vector form in terms of rectangular components. Okay, I hope you can understand. Now what will be the initial momentum? So we know that momentum is equals to mass into velocity. That is very easy. Momentum is mass into velocity. So just multiply mass with this one. So mv cos theta I cap minus mv sin theta j cap. Okay. So this is the initial momentum of the ball. Fine. Now let us find out the final momentum, or the first we will find out the final velocity, and then we are going to find out the final momentum. Okay. So what is the final velocity? Vf. Okay. Here f means final. Over here f means final. Okay. So final velocity. See, for final velocity we are going to see this diagram. This velocity once again I am going to write in terms of vector form, okay, in terms of rectangular components. So you see, what is the x component of the velocity? V cos theta. V cos theta. Now see, this is in negative x direction. See, in negative x direction. So since it is in negative x direction, I am going to use minus I cap. So minus I cap. Okay. Now the y component you see v sin theta. Again this one is in negative y direction. You see, negative y direction. So I am going to use minus j cap. So minus v sin theta j cap. I hope all of you can understand. So this final velocity again I have written in terms of the rectangular components. Fine. Now let us find out the final momentum. So final momentum is going to be, just multiply mass mv cos theta I cap minus mv sin theta j cap. Okay. So this is the final momentum. Now remember what we have to find out. We have to find out the change in momentum of the ball. So you know, change in momentum is final momentum minus initial momentum. So change in momentum, final momentum minus initial momentum. Okay, so final momentum is mv cos theta I cap minus mv sin theta j cap minus this one. Okay, so minus mv cos theta I cap plus mv sin theta j. Now from here you see plus nb sin theta j cap minus nb sin theta j cap will be cancelled. Okay, so the sin theta component gets cancelled. Remember this one. Over here the sin theta component gets cancelled. That means there is no change in momentum along the sin theta direction. Sin theta is perpendicular direction. Okay, so this thing is a very important thing to be remembered. There is no change in momentum in the perpendicular direction. Okay, whatever change in momentum is taking place in the horizontal direction. Okay, it is taking place in the horizontal direction. Now minus nb cos theta I cap minus nb cos theta I cap. So over here you can write minus 2nb cos theta I cap. So this is the change in momentum of the ball. Fine. So this is the change in momentum of the ball. If you want the magnitude, okay, if you want the magnitude of the change in momentum, just remove this one I cap and remove this negative sign. You can get 2mb cos theta. You can get 2mb cos theta. Okay, so this is the change in the magnitude of the change in momentum. Fine, this is the magnitude of the change in momentum of the ball. So this is the problem of the change in momentum of a ball if it is thrown at an angle. Now a special case, what is going to happen if I throw the ball perpendicular to the wall? That means if I throw the ball straight. Suppose over here, this is the wall, and the ball is thrown in this manner. The ball goes and hits with a velocity v, okay, and the ball rebounds back in the same path with the same velocity. I am drawing it down. Okay, don't think that the ball comes down, there is a displacement. No, the ball comes back along the same line. Okay, but since over here I cannot draw, so that's why I am drawing it separately. So in this direction I have thrown the ball, and the ball comes back along the same line with the same velocity. In this case, what is going to happen? You see, if this is theta, and now if I throw the ball straight, if I throw the ball in this direction, so that means over here theta becomes 0 degree. Okay, theta becomes 0 degree. Just you put this particular condition in this equation. So the change in momentum of the ball is going to be, minus 2mb. So cos 0 degree I cap. Cos 0 degree is 1. So minus 2mb I cap. This is the change in momentum, and the magnitude of the change in momentum will be 2mv. Okay, so if the ball is thrown straight, okay, if the ball is thrown straight, that is exactly perpendicular to the wall, then this will be the change in momentum of the ball. Okay, 2mv. If the ball is thrown at an angle theta, then this is going to be the change in momentum of the ball. Remember, if you are writing the magnitude, this is the magnitude, and what about the direction? You see, direction is minus I cap. Okay, and here I am writing directed towards minus x-axis or minus I cap. Okay, remember the direction. So the change in, if this is the wall, so the change in momentum is going to take place in this direction. So that is the minus I cap. Right? So these are the two conditions, and this is the way how to solve a problem regarding a ball that rebounds from a wall at an angle theta, or if you throw the ball perpendicular to the wall. Now I am going to show you one more technique to solve this one. Okay, whichever is easier, you can follow that. Okay, so the problem remains the same. I hope all of you have written whatever I have done over here. So this one I am running. So one more way I am going to show you how to solve this type of numerical. See, so this is the ball that rebounds from the wall. The problem remains the same. Now over here, I am going to again once again resolve it into two rectangular components. Fine. Now, if these are the two vectors, of v, suppose this is vx, this is vy. Okay, I can also write that this vector, if I draw it over here, this is one component. Okay, this is one component, and this vector I am drawing it over here. This is another component. Right? So if you want, I can draw it separately. You see, this is the ball. Right? This is the perpendicular to the wall. This is the ball that is coming. Okay, with the speed v. This is the angle theta. Okay. So this is the angle theta. Now over here I am going to resolve V into two rectangular components once again, but not like the previous case. Suppose this is one, if this is a vector, then this will be one component, this will be another component. Okay, the previous one and this one, they are more or less the same, the division of the components. So this is V cos theta, this is V sin theta. In the main diagram also I am writing, this is V sin theta and this one is V cos theta. Okay, this is V cos theta, right? Okay. Now when the ball is going away from the wall, see, this is the perpendicular to the wall. Okay, so when the ball is moving away from the wall, this is the ball that is moving away from the wall, right? Okay, so this one was theta. Over here also I am going to divide into two rectangular components. So if this is V, this one will be V cos theta and this is going to be V sin theta. Okay, so the same numerical I am doing in two different ways. So over here also again I have divided this one into two rectangular components. When the ball was coming, this is V sin theta, this is V cos theta, and when the ball is returning back from the wall, this is V cos theta and this one is V sin theta. Okay, V cos theta and V sin theta. Fine. Now see, over here, now see, in the previous case, I had taken out the change in velocity or the change in momentum together, that means taking the rectangular components. Over here, I am going to do it separately. You can also do it separately, fine. So, how to do it separately? See, first I am going to take the y-axis. So, y-axis. You see. Now, see, in the y-axis, let us see what are the velocities. In the y-axis, what are the velocities? So, and let us find out what is the change in velocity. So, initial velocity is V sin theta. Final velocity is also V sin theta. You see, in the y-axis, initial velocity is V sin theta and the final velocity is also V sin theta. Fine. Now, over here, I am not going to use vectors since I am using only the magnitude. Now, let us see what is the change in velocity. So, the change in velocity, delta F. Okay. So, this is along the y-axis. So, what is the change in velocity? So, Vf minus Vl. That is V sin theta minus V sin theta. That is 0. So the change in velocity along the y-axis becomes 0. You remember in the previous case also we have seen that the change in velocity in the y-axis it becomes 0. That means there is no change in velocity in the y-axis. So if the change in velocity in the y-axis becomes 0, then the change in momentum also is 0 along the y-axis, because momentum is mass times velocity. Right? So in the y-axis there is no change in velocity, there is no change in momentum. Let's see in the x-axis. So in the x-axis, right? So see, what is the initial velocity in the x-axis? So the initial velocity in the x-axis. Now initial velocity in the x-axis is V cos theta. V cos theta. And the final velocity in the x-axis is also V cos theta. Okay? So final velocity is also V cos theta. So the initial velocity is V cos theta and the final velocity is also V cos theta. You can see this diagram. This is the initial velocity that I have done with red ink and this is the final velocity that I have done with blue ink. Okay, so this is along the x-axis, initial velocity and final velocity. Right? So what is the change in velocity? V cos theta minus. Now see, both these velocities components, they are directed in the opposite direction. You see, V cos theta, the initial is directed in this direction in the positive x-axis. V sin cos theta, this is the final velocity. This is directed in the negative x-axis. Fine. So since one is in positive x-axis, another one is in negative x-axis, so we can write the change in velocity V cos theta minus V cos theta. That becomes V cos theta plus V cos theta, that is 2V cos theta. So this is the change in velocity. Okay, so this is the change in velocity, right? So if the change in velocity is this one, then the change in momentum will be 2mv cos theta, mass into velocity. So this becomes the change in momentum of the ball. And now see, this is the same result that we got using the previous method. So any method you can use, okay, either the previous one or this one. So this one I had done using both the x-axis and y-axis separately. The previous one I had done taking both the axes together, okay, using the rectangular components. So any method which is suitable to you, you can do. So if this will be the change in momentum if the ball is thrown at an angle theta, okay, perpendicular to the ball. If the ball is thrown exactly perpendicular to the wall, that is, if theta is equals to 0 degrees, then the change in momentum becomes 2mv. Okay. So if theta is 0 degree, that means if the ball is thrown straight in this way, then using this you can write, if the ball is thrown straight, then theta equals to 0 degree, then the change in momentum becomes 2mv. Okay. So this one is for if the ball is thrown at an angle theta, this one is if the ball is thrown straight. So two methods I have shown over here. Okay, any method which is suitable to you, you can do. So this is all about the problem regarding a ball which rebounds from a wall. It's a very important topic for your JEE or NEET. Okay, every year 1 or 2 questions comes from this particular topic. I hope all of you liked the video. That was all for today's video. If you have any question, please let me know in the comment section below. If you like the video, please like and subscribe. Thank you.